The tuning fork is creating the sound, it's creating the pressure waves.
So it's basically the same thing as that?
Yeah, well, you said the same thing as that.
As the problem we just went over.
Say again, sorry.
As the problem we just went over?
Yes.
Okay.
What were you reading?
I'm on the test, old test.
Oh,
It's the
okay.
same.
Yeah,
It's the same thing.
it's the same as number 4.
Yes, that's what.
Yeah, so basically, I mean, we've been creating a lot of sound in here, but nothing's really being forced down to the tube. But there we go. It's vibrating back and forth at 512 times a second-ish. And so it's sending pressure waves down, which are then bouncing off the water and coming back, and so you get constructive and destructive interference.
How did you get that number? A 500?
Can't you hear it?
You can tell what it is by hearing
No,
it?
I'm reading it, it's on the side.
Okay.
It'd be cool if I could do that,
For real.
or it would drive me to madness, one or the other.
Okay.
So if I have a 512 hertz, since that's what's right there, tuning fork. I should have wanted to make my NGs a little bit better. Vibrating over an open column of water, or basically an open column which has water in it. There's going to be all sorts of interference patterns going on, but nothing particularly noticeable until you actually get it so that you have the antinode at the very top, which occurs at the first, third, fifth harmonics, basically at the harmonics. So the first harmonic occurs when the distance down to the water and back is a quarter of the wavelength. Because again, full wave. You basically have the two loops there, and this is from a node to an antinode. It's basically from here to here. Oops, can't draw anymore. That's a quarter of a wave.
So will it always be a quarter of a wave?
The first harmonic for one fixed, one free end, or one closed, one open end, is first harmonic will always be a quarter of a wave. After that, all the next harmonics that you would hear, each subsequent one, you would add a half of a wavelength. So 1/4 wavelength for the first harmonic, third harmonic, because there's not really a second one. Third harmonic is 3/4, then 5/4, 7/4, and so on. So if my frequency is 512 hertz, we can figure out what this would be, what that distance should be by, well, I know the speed of the wave is frequency times the wavelength. We know the speed of sound, and we'll just generically go for 340 meters per second. Is equal to the frequency, 512 hertz, times the wavelength. And so the math problem is the wavelength is whatever 340 divided by 512 is. And so the first harmonic will occur at a quarter of that length.
Let's say 0.664.
This is 0.8664.
No, 0.6640625.
Meters. And then a quarter of that,
So do I multiply or divide it?
you divide by 4 or multiply by 1/4, or 0.25.
0.16601565. 60.
Or there's another 6 in there,
Yeah, after the 6.
so 1660 something
15625.
meters.
Somewhere.
From a practical point of view, almost 17 centimeters.
Okay.
And so, in theory, we can hear this get it going first. It should be, oh, there's a kink in there. There we go. And that was the harmonic you just heard. It dies out quickly.
If you use a highlighter, will it be louder? And the expo marker to hit it?
Pardon?
If you use the expo marker to hit it, will it be louder?
Oh. And that is about just shy of 16 centimeters from the top.
When it gets loud, are we hearing like, or what is, like, why does it get louder than quieter? Is it because we're hearing?
That's the antinodes and the nodes, right?
Right. The antinode is here, that's basically what's getting, whatever is at the top is what gets propagated outwards. So the antinode is, you have this quick succession of high pressure, low pressure, or highest pressure, lowest pressure, which means it's gonna hit our eardrums and then pop back, which the signal to our brains is loud, or
Okay.
louder.
So basically, when it's like the third harmonic, it'll be loud, quiet, and then done.
If I started dropping it, if I dropped it at 3/4 of whatever that is, or 3 times whatever that is. And for those of you who have paralyzed issues there, so if I go for 3/4 of this, which is the third harmonic, or 3 times that, which would also be the third harmonic, it would, if I could keep the sound going, it would be loud when I hit the first harmonic as the water level's dropping. Then it should get quiet, and then when I get to the third harmonic, it should be a little bit louder than it just was. And then if I keep going, it'll get loud again at the fifth harmonic.
Okay.
Did I miss the question?
I'm kind of, so like, if you just let a sound like if it was like at that level, whatever, and you just hit it and the sound goes, it would just continue to go, like, it would just, like, what would make it stop going? Like, it would be the first, second, third, fourth, fifth harmonic, like, how?
I mean,
would
if
it
I
just be the third
was
harmonic?
at that, if I figured out where that first harmonic is and just have the water level stay there,
Yeah.
and I hit this,
Mm-hmm.
then it would just sound like,
Loud, quiet, done.
no, it would just sound like a sound. At whatever volume that was. Let's see how close I can get. Not to do metal and metal. Ooh, that wasn't as bad as I was expecting. Don't worry, there's still a chance.
Cause the nodes, it's supposed to be quiet, right? And then at the antinodes, it's loudest.
Yes. It's somewhere around there.
So it makes sense eventually, like, why does it get quieter?
Oh, why is it dropping off?
Yeah.
What the ideal is, it's called harmonic motion, as the tuning fork is vibrating back and forth. Reality is, what's really happening is called damped harmonic motion. There is something ultimately, that vibration that's going through there is ultimately hitting the stand here, and the stand is dampening it. Now you try to hold this back here where it's not gonna dampen it as quickly, but ultimately any vibrations in here will ultimately be felt by this. Plus, it's hitting air. The fact that we can hear it means that some of the energy is being lost into the air.
Okay.
Or it
So,
pushes on the air is pushing back on it, and that eventually causes the dampening.
okay, but if it were like the third harmonic instead of the first, would it be like loud, quiet, and then like end?
It depends on what you mean by that, but from the hand gesture, if I was at the third harmonic, And so I set it up and I had an electronic device creating the sound, so it's not gonna dampen, it basically just uses electricity. If I could, without destroying it, and that's the tricky part there, if I were moving down the air column, it would be loud, and then it would be quiet, and then it would be loud, and then loud at this point, and then quiet again. If I could travel down there.
So it would be loud, quiet, and then the sound would, like, would the sound end there, or would it?
Well, then
happen
you're into the
again?
water.
Oh. And that's a different situation.
Yeah, so now you're dealing with, a pressure wave entering a new medium, and frequency would stay the same, but the speed would change and the wavelength, therefore the wavelength would change.
Okay, so it wouldn't be like loud, quiet, it wouldn't just like continue to the fifth harmonic, the sixth harmonic, it wouldn't just go, or I guess there's no fifth, it wouldn't go like loud, no, there's no sixth. It would go like loud, quiet, like it wouldn't continue indefinitely?
No,
Okay,
no, and the other part of that is the third harmonic, if I could get the water level so that we have the third harmonic, that is not as loud as the first harmonic. Because also while it's going down, it hits the water, but also it's bouncing its sides more, and there's just more stuff absorbing.
okay, thank you.
Is there?
Can you do 10C for me?
Say 10E,
No, C, 10C.
10C. Speed of the sound?
Yeah, of the whole experience.
All right, so that is going back to this formula right here. Now, in the master set problem, I told you the frequency, you found the wavelength, and then calculated the speed. What I did right here is, we started with the speed and the frequency, and you found the wavelength. So, you know, any of these type problems, you need two of them in order to get the third.
Yeah, so divide. Would I divide the, frequency with the, sound?
If, in this one right here, since I was solving for wavelength, I would divide the speed divided by the frequency.
Yeah, frequency, yeah, speed divided by frequency, okay.
In the master set problem, since you're given these two, you multiply them in order to find speed.
Okay, I see what you're saying.
Did you need me to work through part C now, or you're feeling good?
So I would take the wavelength from the sound of the tuning fork that I got, well, that answer, and then multiply it by the frequency. Which is
The-
25.
Word that again?
So I would take the wavelength of the sound from the tuning fork that I found and multiply it by frequency?
Yes.
Okay.
Yeah, so your answer to part B times the frequency that's given in the problem.
Okay, I see.
Other question?
Is the test gonna look like this master set?
You will notice some similarities.
For the last test that we took, did all of us get another question right besides the first one?
Yeah, there were two questions that were actually got right.
So will you do the worm?
Yeah, the deal was never struck.
I did try to strike it though.
You did, and, I said, my memory is I said, talk to me later, and you didn't. So I feel no obligation to do the worm. Although I was tempted to, and, just as a surprise, and then realized that if I did it without practicing enough, I probably would hurt myself pretty badly. And so I thought, let's just not do that quite yet.
Oh, I have one. How do you increase the harmonic?
So when I was out in the hallway, and so I was just moving it back and forth. To increase the harmonic, I just moved back and forth more rapidly. In essence, I increased the frequency,
Okay.
or kept the amplitude the same and increased the speed of my hand.
Okay.
But with our lab, to increase the harmonics,
It was
we
less.
added more mass.
Less.
To increase the harmonic, you less mass.
Yeah, you're right, 'cause one took a lot.
Uh-huh. So,
Okay.
So it happens, in essence, what you're doing there is by reducing the tension, so reducing the mass reduces the tension, which reduces the speed of the wave. And so the
So
wave doesn't
reduce-
travel as far in one period before the next one's created, so you create more waves while that first wave is going down, you can create more waves come up behind it
So reduce tension.
by reducing tension. You can also reduce the speed of the wave by increasing the mass of the string.
Okay.
Or mass per unit length.
How do you increase the wavelength?
If you can maintain the speed, then you can increase wavelength by decreasing frequency. Or, since wavelength is how far it travels within a period, the period being the amount of time it takes to create a wave. So I could also keep the frequency the same, but increase the speed of the wave.
For this
So it would
question,
be by adding tension or reducing the mass per length.
for this question here, you answered it a different way in the old test than in the way you answered it here.
Okay?
Before you just, multiplied the harmonic by the length of the wave, or by the length of the wavelength, or the harmonic by the wavelength, instead of subtracting it.
Oh, here?
Yeah.
Well, I'd have to go look to see what I did.
This is what you, or what you.
Did I get the same answer?
No.
No, okay. I'm feeling confident with this, I just don't remember what I did on the other one. So which test was that?
It was summer 2013.
What number was that?
It was, number. It was the first short answer, sorry. It was the fourth short answer on February 2013.
Alright, at some point I'll take a look and see if there's a mistake in the answer key there, or solutions, whichever one it is, I guess solutions if I worked it out. Is there okay? Thank you for letting me say.
what kind of answer were you looking for in 6A, increase the speed of the wave in the rope?
Alright, so a number of people for that one, again, we have our two formulas here. Because we are dealing with a long rope, so the length is much bigger than the thickness of it, we also have the other formula here. Now, a number of people talked about increasing frequency or something like that, but unless I change something else, if I increase the frequency, I'm going to be dropping the wavelength, so that the speed stays the same. Because the speed of the wave is dependent upon the physical structure of it, as well as the tension. So I can either increase the tension to increase the speed, or reduce the linear density.
Okay.
So increase the force the rope exerts on itself, or decrease how much mass I
Change
have
the
to
rope
move.
altogether. Okay, that makes sense.
So either decrease tension, or increase tension or decrease tension?
Well, I got a fraction here, so to make this bigger, I need to make this bigger or that smaller.
Okay, so increase tension or decrease linear density. Thank you.
Other questions?
Would you just say the opposite for wavelength? Would you just say the opposite if you were trying to increase the wavelength? That you would decrease your tension and increase
Oh.
your linear density?
If I want to increase wavelength? If I want to increase wavelength, I want the wave to travel within the amount of time of creating a wave. I want it to travel farther. If I'm going to increase wavelength, which means I have to increase the speed.
Oh.
Assuming I'm keeping the frequency the same.
Okay.
Could you also just decrease frequency?
Also decrease frequency?
Yeah, like instead, like to increase wavelength, could you decrease frequency?
Yes, assuming I don't change anything else with the medium. If these stay the same, then decreasing frequency will increase the wavelength. You're basically increasing the amount of time it takes to create a wave, so it gives it a chance to go farther.
Why couldn't you just make the rope longer?
Say it again?
Make the rope longer?
Oh, all right, so on the string vibrator, you had, let's say that you have the third harmonic. There's a set wavelength there, and there's a set frequency for whatever the setup is. There's a set tension and so forth. I can create if I decrease the wavelength, so let's say I change the wave to that, I'll see a second harmonic, but I haven't changed the wavelength actually, and I haven't changed the frequency at all. I haven't changed the speed of the wave. All I've changed, so changing that would change the harmonic, but it doesn't actually change anything physical about the wave. The tension stayed the same, and that stayed the same, so V's the same. The string vibrator in this particular case is still moving up and down at 60 hertz. And so just changing the length is not enough if you want to change the harmonic, if you want to change the wavelength or the frequency.
Makes sense.
And I've seen people do this on the string vibrator lab where, oh, we need another harmonic, let's just move this farther away, and lo and behold, another one appears. But what happens when you get the graph is you get basically the same point over and over again, because the tension doesn't change and the wavelength doesn't change.
So, if you change the wavelength, it doesn't change the speed or the,
Not in and of itself, right?
so it would change the frequency or no?
If the speed stays the same, in other words, the physical attributes of the rope, if the tension and the linear density of the rope stay the same, then I increase one, the other one drops.
Okay, good. So then, okay, never mind, you answered my question.
Okay.